Welcome to this webinar on online cable failures, ultimate causes, and detection methods. We are a UK-based company that has been around for over 50 years. We specialize in asset reliability, electrical asset reliability, and we do a variety of things from consulting to building equipment to doing surveys and oil and gas analysis and all that. And not all that's relevant today. But there are a couple things that are. One, we maintain a large, highly qualified forensic failure lab. So customers from around the world send us cable terminations that might have failed, or switchgear that failed, or have us go out on site to look at a transformer. And we do a lot of this work, and that allows us a lot of insight into how assets fail. And that's part of this discussion today, with some of the results of what we've gotten are analyzed. The other thing I want to bring out is we do manufacture partial discharge survey instruments and monitoring systems. We'll talk very briefly about that at the end. This won't be a sales presentation, but the last couple minutes will be about some of the technologies we use in our measurements. And so that's all you need to know about EA technology. If you want to learn more, you can go to our website. So I don't want to spend a lot of time on what partial discharge is in this webinar. I did cover it in great depth in the last webinar, and if you'd like to see that, it's on our YouTube channel. It's a similar hour-long thing on partial discharge. Why is it, and how do you measure for it? But I will tell a little bit to bring everybody up to speed. Partial discharge, and this is the IEC 60270 definition, that it is a localized breakdown of the insulation. So if you think of the insulation system from the conductor to ground, a complete discharge would be a flashover, a catastrophic failure. But it is possible for part of the insulation to discharge and actually have a spark and have a current flow, but it doesn't bridge the entire gap. And that's what we're talking about today. This can cause a variety of effects. Some that were useful because we can use it to detect it, some that are harmful that cause failure. And that's the textbook definition of partial discharge. I like to describe it for people using this slide here. It makes it a bit more apparent, because for years and years, decades, people thought partial discharge, well, it's voodoo, it's black magic, it's not real, it's kind of a side effect. Just want to explain technically what's going on when you have discharge. So I got a picture here of a conductor and a ground with some sort of insulation medium between it. So that green thing on the slide is the insulation. And we have a discharge site that we've got in red. Now, any insulation system can be modeled as a set of series and parallel capacitors. By its definition, you have a conductor and a ground, you have two plates with an insulating medium between them. That's the definition of a capacitor. So everything in our system has capacitance, some of it less, some of it more. If you've done any work in protective relaying for cables, you know that you have to allow for the charging current. Well, that's a 60 hertz current or power system frequency current that is going through the capacitance of the insulation. And it can be substantial, it can be a couple amps. So you need to realize that we've got this capacitance everywhere, and that's where we have this issue. So looking at this model, I've made it simple on myself. I've got three capacitors. They're the exact same value, and they are in series from conductor to ground. C2 is representative of the discharge site. So this is a point in the insulation where the voltage across that capacitance cannot be withstood by the insulation medium. So because of a void or crack or dirt or something else, we cannot withstand that voltage. So if we look at it, say 3 kilohertz peak sine wave, we're going up to 3 kV, and as we do, the three capacitors divide evenly, and you have 1,000 volts across each. Let's say this void can only withstand 999 volts. So when you get to 1,000, it flashes over. The voltage across C2 goes from 999 or 1,000 to 0 as quickly as possible. So what happens is you get a little blue spark, you ionize any gases in the area, and this collapses down to close to 0 volts. But I still have 3,000 volts between my conductor and ground because I've got good stiff sources. So that means C1 and C3 have to both go to 1500 volts each. In order to change the voltage on a capacitor, you have to flow current. That's basic laws we all learned. So what partial discharge is this current flow as a result of the insulation section to not withstand the voltage applied to it. So we get a current pulse that's equalizing the voltage on the capacitance. It is unipolar. It is very fast because we're talking about small capacitances. It's typically a couple of microseconds, and it's unipolar, and then it's going to go from one direction or the other depending on the polarity of the sine wave. There can be some ringing at the end, but it's largely unipolar. So that is the science of partial discharge. It's a real current. It can be measured. It follows Ohm's law. It wants to find a path to ground. It is not voodoo or black magic. It is real, and that's what we're going to focus on today. Discharge can occur either on the surface, through air, internally. Here we've got a picture of internal discharge. We've got a void inside this insulation layer, and we've got a little video here which shows the actual spark and the current flowing that we can see. This is real discharge is occurring. The black tracking on there is indicative of the surface discharge that you see. That's a carbonized track left by the discharge. This is very typical of failure mode. This is very close to failure. When we talk about discharge, we like to talk about three types, break it down into three types. And corona discharge is the most common. It's also the least harmful. Lots of people throughout the world interchangeably use the term corona and surface discharge, or corona and partial discharge. But corona discharge is where this current path is through a gaseous medium, typically air. So when you get into the EHV transmission lines and insulators and that, without a perfectly uniform field, there are spots on that conductor, air molecules will not be able to withstand the field there. So if you had a sharp point or a bolt sticking out or some sort of narrow geometry feature that's going to cause a concentration of field, the air molecules right around that point are not going to be able to withstand the voltage field. So what happens is they discharge. The air molecules become ionized. They break down into their component parts, oxygen and nitrogen mainly, and you can see the streamers at night. You can see them with a ultraviolet camera. The thing is, we're destroying air molecules. That's the insulation we're destroying. Fortunately, those are replenished by adjacent air molecules, and you don't get a buildup. You don't get a worsening. You don't get a catastrophic failure over time as a result of corona discharge. So when we're looking at it, we need to know it's there. We need to be aware of it. We need to make sure that it's not one of the other discharges that we're looking at, and vice versa, because you don't want to fix something that doesn't need to be fixed, and you don't want to lead to a false positive of that. So the second, and is the most common and the fastest moving, fastest growing partial discharge, is surface discharge. So this is characterized by the current path is the interface between the insulation and air. So as you see here in this picture, and this is 6-year-old switchgear, you get this tracking across the surface. What we saw in the video in the last slide, that surface discharge, the current is trying to find a path to ground. While it's doing that, it's damaging the insulation. It's leaving a carbonized track behind it. That carbonized track is conductive. And because it's conductive, the voltage appears at the outer edges of those branches. So now we have voltage where we didn't think we should, where we wouldn't have it by design. So we're more likely to encounter arc flash when things move. So that's another side effect of partial discharge we need to be careful of. The last picture is internal discharge. So this is where you're not on the surface. You have this discharge effect. It's slow moving. It takes a long time to lead to a catastrophic failure. This picture here is a cast resin CT that probably took decades to eat that channel through it. But the problem is you can't see it. You can't inspect for it. You can't take it apart. If you take something apart and you inspect it, you don't see anything. You put it back in service, it could blow up the next day due to internal discharge. So unless you're doing partial discharge tests, you might not even know that you have discharge until you know. So when you have partial discharge, there are a number of effects, some good, some bad. The first effect I'm going to talk about is heat. Now, partial discharge is a very low energy event. It does not involve a lot of watts, so you don't have a big heat impact, but it is a very high temperature. So those are not diametrically opposed. It's plasma. It's very hot. By its definition, plasma is in thousands of degrees, but there's not a lot of caloric energy in there. So what you get is local to it, you might damage the insulation. The molecules, a couple molecules of insulation maybe on each spark get damaged. It's slow moving, but that heat is going to damage the insulation. Worse, if you're on the surface and you're exposed to air, I told you that air breaks down into its component parts, basically ozone and nitrous oxide. Ozone comes from the oxygen, nitrous oxide from the nitrogen. Nitrous oxide isn't all that bad by itself, but when you combine it with any kind of water, humidity, salt, humidity, even worse, it creates nitric acid. And that nitric acid is going to eat through just about everything we use in our power system. Not so much glass and ceramic, but it's going to eat through XLPE, it's going to eat through PILC, it's going to eat through that red panel board and that red resin that we like to use so much. So what happens is, as a result of the heat and a result of the nitric acid, we get this discharge gets worse. And the void gets worse, which means the discharge works, which means more side effects, and you can see how it will snowball until it eventually leads to a catastrophic failure. Discharge may stop when the voltage goes down or the humidity goes down, but it's not going to heal itself. So when those proper conditions return, the discharge is going to start up, and that's going to keep going until it fails. Now, there's a couple other things that happen that we don't really care too much about. And one is acoustic energy is generated. So this is sound waves traveling through air, traveling through liquids, traveling through solids, but they're sound waves. There is a certain amount of it in the audio band, but there's a lot more in the ultrasonic band. So ultrasonic is above the range of human hearing. Audio is within the range of human hearing. In the ultrasonic band, there's a lot of very characteristic noise from surface discharge, and we can use that as a non-contact, non-invasive way of testing for PD. In the electromagnetic field, we already talked about heat, which is the UV or the infrared rays. You get light, which is in the visible spectrum. As you saw in that video, you can see the sparks. In the radio spectrum, we get a lot of radio emissions. If you've ever had an AM radio, for those of us old enough to remember AM radio in your car, your truck, in a lightning storm, you get a lot of sparking and arcing and that impacting the radio. So we can use these radio waves to detect PD as well. Now, a lot of our power systems, cables specifically, shielded cables specifically, metal-clad switchgear, transformers, they are surrounded by a Faraday cage. So we don't get the radio waves out of them that easily. So radio has its place more in open air substations, but it's a good way of detecting PD. TEV is something I'm not going to spend a lot of time on, but this is a voltage effect that occurs on the outside of switchgear, on the outside of cable shields. It's a voltage that appears on the outside of a grounded metal conductive casing, a Faraday cage that's grounded. There's an actual voltage that you can measure. It's a result of the discharge inside. That is a non-contact way of detecting PD. And then the last one, which we're going to spend a lot of time on, is this current. We've got a thing called a radio frequency current transformer. It can detect the number of electrons going through the bore of this toroidal transformer. And what we can do with that is, if we can detect those electrons and count them and graph them and so forth, we can find PD going down a certain path. And that's really helpful with cables, where we can put this on the ground shield, the ground strap of the cable, and detect the PD. Lots of things cause PD. Workmanship is by far the number one, and not workmanship in a negative way. It's not people intentionally doing a bad job. It's not people that don't want to do a good job. But you get workmanship issues where people are not trained. They don't have the right tools. They don't understand the importance of cleanliness. and that's a failure of the people giving them the work, the management. So that's a big issue. Contamination. If you are anywhere near the ocean, salt air, salt humidity. The islands in the Caribbean and Bermuda, they all suffer terribly from salt air, humidity, and that causes a lot of problems. If you have pollution from maybe your facility, if you're an oil refinery or that, even though your pollutants or your contaminants may not be conductive, they attract and hold humidity. They hold moisture, and that moisture makes the surface conductive, which then changes the field strength, which then can cause PD. Damage, of course, anything that's going to damage the insulation can cause it. Age, some materials, not so much the solid state materials like XLPE or that, they don't age too much, but PILC, the oil can migrate away from certain high spots in a cable and leading to PD. And then design. Doesn't happen very often, but you'll get components that are not designed well, or they're designed such that they're so hard to install that they're never installed correctly. That's kind of halfway between workmanship and design. But if it's too hard to install, then you shouldn't be using. So these all contribute to cause PD in the field. Next topic I want to touch on is, why do we use shielded cables? When I got into the power business, I had no idea why we use shielded cables. I understood why we use them for instrumentation, but why do we use them? Why do we need them on an 11 kV cable or a 33 kV cable? Why in the world do we need a shield? We're not trying to keep noise out of the conductor. And if you look at typical cable construction, you've got several layers. They're all kind of the same. But what you have is you have this conductor, and then on top of that is a semiconducting layer. And that semiconducting layer is there to smooth out the field. So your conductor stranded, so it's got bumps on it from the wires, and those strands would cause an unequal field. So we have a semicon layer to smooth that out. Then we have our insulation, and then above that insulation, we have another semicon layer before we get to our outer shield, or our concentric neutral. And the idea is we're going to use that to smooth out the field at that side of the insulation. So we have a smooth field inside and outside, so we should have a steady gradient of electric field across the insulation, which is what we want to do. And this is how the cables are designed. They're manufactured this way. Unless you've got a major error, gross mistake in the manufacturing process, that should be pretty well controlled. The reason we do this is so we have this field, we can engineer this field, we can design this field to stay within this cable and not be affected by outside influences. If we didn't have a shield on the cable, we would have no idea how the field is until it's installed. By putting a shield and making the shield part of that cable, we can tell what the field strength is going to be, make sure it's within the capability of the installation, and we're all set. So if there's something outside the shield, like this support brace that I've drawn here, if that's there, it doesn't affect the equipotential lines. Those field strength lines stay the same distance apart within the capability of the insulation. Now, if we put something out without a shield, we get this type of situation where we have the field is not contained by a shield, and if you have some external device, even if it's not conducting, it can cause a concentration of field stress. And I use this picture specifically because it looks a lot like this picture. So this is a real customer. They have 33 kV cable. They used unshielded cable to go up to their PTs, and they draped them across this insulation. They high potted it to some 60 kV and didn't have a problem. They thought they were good. Instantly, on energization, partial discharge started. These cables and these burn marks on the cables are after 4 months of operation. And they had done every test they thought they needed to do. Fortunately, this customer had a full-time PD monitor. Within 2 months, they were able to detect the PD, and 2 months after that, they were able to get a shutdown and revise this. This installation was approved by the switchgear manufacturer. That was the first person they called, and that was okay according to the switchgear manufacturer. So not everybody really understands the whole idea of field stress control. On cables, let's look more into cables. We've got this engineered system for the length of the cable, but then at the end of the cable, we cut the shield off, and we've got to get the conductor out into open air. In order to do that, we've got to take special measures to allow the field strength to not exceed the capability of the surrounding, whether it's the insulation, whether it's air, whether it's the termination itself. We've got to make sure that that field never exceeds the withstand capability. Otherwise, you're going to get discharge and you're going to get failure. 40 years ago, we had tape stress cones that were done by artisans who had long internships and mentorships that were real experts at it. Then we went to cold shrink termination, or hot shrink terminations, and people use torches and that. And now we're into cold shrink terminations where anybody can do it. And that specifically is the problem. People think that anybody can do it. A cold shrink termination is a great thing, and used correctly, they're wonderful. But the problem is they appear easy to use. And if you go to Amazon and you buy a Raychem termination, and it comes with a 4-page instruction sheet, and you go and say, okay, I can do this. And the instruction sheet says clean cable as usual, or strip semicon layer back cleanly. What does that mean specifically? It means something different to you than it does to me, and that's where we get ourselves in trouble. So there's a variety of different stress control structures out there. Some are easier to use, some are harder to use, but if they're not used correctly, we get discharge. And that's where we're seeing more and more discharge every day, because people without sufficient training and tools are doing terminations because cold shrink terminations appear to be easy to do. That's one of the findings we have. So these are all examples of field stress where it's failed. Here in the upper left is a semicon layer that is cut back terribly. We have a couple areas where the unshielded cables are too close together or too close to a brace. Or in the lower right, we have an insulation that was cut back too far from the clamp, and that gap allowed for discharge. So why do we test cables? Why do we want to test cables is the next topic. Well, one of the reasons we want to test cables is because of operational reasons. So this is the guys in the trench. They got to keep the facility running. They keep the utility running. They want to do as little maintenance as possible because they've got more maintenance than they've got people to do. So if they can test cables and extend them intervals, that's good. But if they can't extend the intervals, at least they can prevent failures. And of course, number one on our list is going to be safety. So if we can improve safety and avoid catastrophic failures, that's even better. On the other side of the equation, you've got the asset manager. He's responsible for a portfolio of devices and work orders and replacements, and he wants to make the best of his time and money. So he's going to manage the risk. What he might want to do is look at condition, make decisions on that based on criticality, and determine when things have to be replaced, when they need to be repaired, or when they need to be tested more frequently because they're critical and they're starting to show something. So they will play all these games, and their main goal is to reduce capital expenditure, of course, looking for improved safety and preventing failures as well. So you got two different groups that benefit from assessing cable condition. The obvious reason to assess cable condition is I've got this picture. If I found something wrong with this as a result of the test, I would much rather fix it now than fix it when it looks like this. So here's a termination that didn't quite make it to repair in time. Obviously, that's going to be a lot harder to repair. One of the biggest questions we get, most common questions we get is, well, okay, I detected PD, how long do I have till it fails? Or how often should I be testing for PD? No one that knows anything is going to give you a definitive answer for that. It depends on your criticality. It depends on how long the PD is going to go from the start of the PD to the detection point to the point at which failure occurs. We can't always predict that because we don't know, we haven't taken the system apart to see how fast it's going to progress. What we can do is look at detecting or doing surveys more frequently on critical assets. If you've got something that's feeding your factory, and if that cable goes down, your factory goes down, well, you really want to look at that pretty often, and even more often if you're starting to detect a low level, you might even want to put in permanent monitoring if you really have a few critical non-redundant cables. If you have cables that might affect part of your production, or you have cables that have redundancy, that's good. You can do a little bit less testing on those. And you may have some that are low consequence. But you need to make these decisions, and the only way you can make those decisions is to have data, and the data you get from testing. So why do cables fail? And that's the big point of this webinar today. Is we did a study of cable failures as they came into EA's forensic lab. And we looked at the last 100 forensic analysis reports we did. It was only 5 years worth, 4 years worth of reports that we looked at, and there was 100 in there. And unfortunately, 27 of them were not relevant. They were either lower voltage or a mechanical failure, or something that didn't lend to medium voltage cable failures. So we looked at 73 reports, and these are reports that have been done over a recent period. And we looked at them, how long did it take to fail, what type of insulation, the voltage, where were they installed, what failed, and we spent a fair amount of time on the proximate cause and the ultimate cause. Proximate cause being the immediate thing that caused the failure. The ultimate cause is a little bit further removed, and I'll talk about that a little more. First thing we determined was they do have a relatively predictable failure curve, and it looks like the failure curve that you would see from anything else, typically called a Weibull distribution. So you have an infant mortality period, you have then a longer period of random failures, and then as things get toward the end of their life, you get more failures that would be considered end of life. So we broke this down into 3 groupings: our infant mortality, random failures, and end of life. Now, in all electrical and electronic devices have this type of curve. Infant mortality on some things is 10 seconds, 10 minutes, 10 days. We're looking more at 10 years. Random failures take life. This is your standard cable length life to 40 years. After 40 years, we start to see the failures increase. Makes sense. So a lot of this study just pointed out things we all thought were the case, but we actually had some numbers now. We looked at the different types of insulation. This is more representative of the types of devices that were sent to us. It may not mean as much, because if you look at EPR, which is the rubber-based insulation, that was only 1% of the failures. I don't think that means it's 1% of the failures in the world. I think it's just that people sent more XLPE, and if you look at it, it's disproportionately low compared to the amount of installed EPR in the field. But XLPE is one of the biggest ones, and that's the cable we're all putting in today. So it's a real problem for new and recent installations. We look very closely at where did these failures occur. And you look at this, we've got the connector, the termination, the splice. These are all places where the technician was handling the equipment. Something was done to the cable at these points in the field. Mid-cable, that's why as it comes out of the factory, yeah, it's impacted by some of the environment around it. We see sometimes that rocks and buried cable, rocks will migrate up and press in on the insulation, cause a failure, or undersea cable, you could have a water problem. But for the most part, 75%, the fault location was where someone was touching the cable out in the field. Then we looked at the proximate causes, and proximate is, why did it fail right there? What did it break down? So these are the answers that the different scientists put on the reports. And I've got a little picture of the Titanic there. The Titanic sank because it's filled with water. That's the proximate cause of the sinking, is that it filled with water. Just like moisture, input, overheating, all these are proximate causes. But it's very hard to say I'm going to address these 15 things and come up with some overall solution to these 15 problems when they have different ultimate causes, perhaps. So we use a technique called the 5 whys, and we looked at each level of why did that happen, and then why did that happen. So to take the Titanic, well, the boat sank because it filled with water. Well, why did it fill with water? Well, it hit an iceberg. Well, why did it hit an iceberg? Well, it was going too fast. Well, why was it going too fast? So you follow that back to the ultimate cause. The ultimate cause was that the White Star Line management was showing off, and they wanted to have the fastest voyage across the Atlantic, and that was their problem. So if you were to fix their iceberg detection, or if you're able to fix how much water they contain, you might solve a problem here and there. But if you don't change the attitude of the management, that could result in some other proximate cause causing a failure. So you always want to address the ultimate causes, not the proximate causes. So when we get to that, we then looked at what are the ultimate causes. So for these 73 events, we looked really what's going on. So we see results that didn't really surprise us, that workmanship was 2/3 of the failures. One surprise was the manufacturing defects in the accessories or in the cable were 16%. That's high. We really expected to see that lower, and expected external damage to be a bit higher. 4% was not very high. So if you look at that, if you could get rid of the manufacturing defects and you could get rid of the workmanship issues, you'd have 1/10 the number of failures that you have today. So those are the ultimate causes we want to address. So here's a couple examples from our study. I had a college student, cheap labor, go through and analyze and read all of these reports and generate some of the data here. And what we found, this is a PILC to XLPE adapter, and it lasted 1 hour. So they high-potted it, they energized it, walked away, and an hour later they were back. And what happened was, if I go to the next slide, it wouldn't have lasted long if that failure. So this is where we get into proximate failures being the issue. The failure occurred mainly because of this 30-millimeter gap between the end of the insulation and the barrel of the joint. You had discharge raging that it caused a flashover. You didn't need much partial discharge. It almost flashed over on energization. But that was just one cause. You can see the picture in the middle and the bottom. They only had one shear bolt making connection. That joint would have overheated. They didn't put any putty in the shear bolt holes. That would have caused a low level of partial discharge that would eventually led to failure. Tubes were cut badly. Insulation was negative. Lots of workmanship issues. I use the term horrific. It was horrific. And, you've got to address these sort of issues. Fixing one of them or two of them would have still led to failure. Here's another example. Here's a cable. It lasted 18 months. That's long in some circles, but we would all expect our cables to last more than 18 months. And it was at a splice and led to a pretty quick failure. When this was taken apart, we again found the proximate cause, which was the sharp edge of this shear bolt. So those of you who don't know, a shear bolt is used to press down on a connector, and when you have a sufficient torque, the bolt shears off. Well, they didn't deburr the edge of where that shear bolt snapped off. So they didn't know that. They didn't understand the instructions, and they left the sharp edge, which cut into the insulation, caused discharge, and then failed. But there were, again, terrible workmanship and other issues. If you look at the insulation up here, they dug pretty deep into it when they took the semicon layer off, but they didn't clean it up, and there was sand in the joint. All these things would lead you to discharge. But if you didn't know that you had to have a perfectly smooth installation, and you didn't know that a little bit of sand like this could be a problem, you would think you did a good job. And here we are 18 months later fixing the cable. The last example in here is a midspan failure. This was a cable that lasted 28 years, which is good. It's not fantastic, but it's good. And it failed in the middle of the cable. And when we did the examination and took some micrographs of it, we saw both electrical trees and water trees in the insulation. Now, these were leading to discharge, which eventually caused a failure. What this points us toward, okay, there was no defect of workmanship. There was nothing that we could have done on the outset. But if we had done more testing of this cable, periodic testing every couple of years, we might have known that there was a problem brewing and been able to address it on our time frame as opposed to waiting till it failed. Now, from an asset management point, you may decide to let it fail, but at least you're making an informed decision. So testing helps you find things even when there's no workmanship issues. Part of the report process is to look at what can we do to make things better, right? There's no sense doing a report unless you're going to do something about it. And so we look at what can we do on new installations. Well, if your workmanship is an issue, you've got to have joiners that are better trained. You've got to have better instructions. You've got to have better procedures. Make sure they're using the right tools. Make sure the instructions are clear, because what you write and what I write, what I read may be different. So you got to make sure those are all clear. You also want to talk with the manufacturer. You know, we did have some manufacturing defects. You also want to make sure that the manufacturer agrees with your procedures and that you're doing everything that you can. You know, it's in their best interest that your cables don't fail. The last thing you want to do is put something up on an e-car or some other fault notification that you're having a problem with termination X. So they will help you out. Also look at the equipment selection. Classic example is hot shrink tubing. Takes a little bit more skill to do those terminations and get the tubing smooth and then do the torch work safely. You know, maybe you go to cold shrink. Doesn't mean it's that much easier, but it's less likely to be done wrong. Now, we've got new installations, but we've also got a lot of existing assets. We've got millions of existing cables out there, and they're hard to get to. They may be buried under a street. They may be in the 50 feet in the air in a refinery. So what can we do? Well, you can get to the ends of the cable. You can do partial discharge testing. That's the number one recommendation that we came up with, because that will give you an indication of the cable quality. You can do tan delta testing. You can do high pot testing, but those require an outage, and an outage nowadays is pretty hard to get. So PD testing can be done online, and that's why that kept popping up. If you're going to take something offline, then you would want to do PD, you want to do Megger, you want to do tan delta and withstand tests. You got to be careful with the withstand test that you don't damage it even further. You want to look at the condition of similar systems, similar cables, similar terminations. If I'm having a problem everywhere on the same type of termination, I can start doing some asset management and looking where I've got those terminations. Again, the manufacturer is one of your best allies, and visual inspections of terminations, it will show that surface discharge. So that's a really good thing to look for. So that's our study. What we came out with from that study was that cables have a relatively predictable reliability curve. A third of the cable failures occur in the first 10 years, which is pretty high, probably getting higher, I would say. And most of the cable failures occur in the terminations and the splices due to workmanship. So we need to look at that. Many workmanship issues can be improved through training, but you can't fix everything. Here's a picture from one of our failure investigations. The joiner did not know what to do with the white tape. So he found something to do with it, probably not the best use of that tape, and that joint failed, not surprisingly. But that's out there. We've got those things out there. So how do we live with all these mistakes that are living out there now? We have to find a way to live with that. So I'm going to take a break now, and if Tim, you want to read me off any questions that we have so far?
Yep. First one is, are there any online monitoring technologies that help to predict failure?
Well, yes. As I said, cable monitoring for partial discharge, whether it's a periodic survey type or a 24/7 monitoring system, both of those will tell you if you have any discharge going on in the cable, and you can watch it and track it and take action at the appropriate time.
What are the units utilized for measurements?
I'll get into that further down. That's the next section, is how do we do this monitoring, and so I will cover that later.
The overabundance of XLPE in the study, could that be an EU install bias?
It certainly could. Again, we worked with the data we had. We did not find a good explanation why EPR was so low. These were largely EU cables. So if they're installing more XLPE, it might be a good explanation for that influence.
Question about access to the slides. The slide deck and the presentation will be sent out in a link afterwards for everyone to get access to them.
That's correct. We'll be giving everyone the presentation, and because we're recording, we'll also give everyone a copy of the video once it's edited and all my stupid comments are removed. So look for emails from us probably next week at this point.
Were the manufacturer defects in older cables earlier manufacturing methods?
I don't have that information available. These questions, I will also provide you with written answers to the questions that will be better thought out than my off-the-cuff answers. So I'll look into that and see if I can get you an answer.
And that looks like the last one for now. We will have another question section at the end. So if you just type it into the chat, we'll catch up to it. We'll cover them at that time.
Okay. Now we're going to talk a little bit about how do you test for partial discharge online. The problem with cables, and you all know this if you're in this webinar, the problem with cables is I can't see inside them. I can't see them for most of their length. Lots of people use buried splices as shown in this picture here. I may not even know where those are. So the problem is I don't have access to the cable. I can't look at it. I can't test it along its length. So one thing you can do is if you can get to the ends of the cables and you can run a test from the length that covers the length of the cable from one end or from either end, that's going to make things a lot easier. Unfortunately, you can do that with partial discharge. When you have partial discharge in a cable, remember back to my picture with the 3 capacitors. I've got a conductor, I've got the orange is the shield, and I've got a void in between them, and I've got a discharge current. That discharge current is going to travel down the shield, through the insulation, and then down the shield into the earth ground. That's how the PD is going to travel. So if I can put some sensing device, what I'm going to call an RFCT or radio frequency current transformer, around that ground strap, I can measure that current. And I can look at the shape of it. I can look at where it's occurring. It's going to give me a lot of information, and it'll help me find PD, even though I may not be within a couple kilometers of the actual discharge site. So what is an RFCT? So it's a current transformer that's designed to pick up PD specifically. It does not pick up power system frequencies. So at 50, 60 hertz, it's immune to that. And that's important because you can have a fair amount of that current flowing in your shield. If you have an unbalance in load, you could have 100 amps flowing through your shield. And we're looking at microamps here. So we have to make sure that the measuring device is not influenced by the low frequency current. So these typically don't pick up much below 100 kilohertz. So 60 hertz and all its harmonics are not going to be an issue. We want to mount them to the shield, not to the conductor. If you put them on the conductor, then you've got thousands of amps perhaps that you need to reject. And that's a lot harder. You also have safety issues. So I can put it on the ground shield. I'm good. Variety of different sizes, shapes, indoor types, outdoor weatherproof types, permanent install types, and temporary install types. We also have a shotgun mounted version that opens and closes that you can use, and say you're on a riser pole and you want to clamp that on and you want to keep your head and your arms away from the termination as far as you can. That can help you out. Different installation gives you different challenges. For those of you lucky enough to work with IC type switchgear, where the cables typically are, the ground shield is removed outside the high voltage compartment, and there's a gland, and the ground straps are available out in the open air. This picture on the upper left shows that type of installation. You can walk up with an RFCT, clamp it on, do a test in a shirt sleeve environment. Life is grand. These pictures on the bottom show more US style gear where the ground straps are inside the high voltage compartment. And this one in the center and the top is also a US style where they've got multiple conductors per phase. it can get real crowded in there. Lots of ground straps and tight fitting. But what you can do for the US style, or you could do it for the IEC, you don't necessarily have to, you can permanently install those RFCTs and leave them there, bring their connections out to an outside connector, and then you can walk up and do a test in a shirt sleeve environment anytime you want. Picture on the right is at Detroit Airport. It's a 220 kV cable. They had a splice put in just where the ladder is because it blew up, and they wanted to do a cable test to make sure the splice didn't have any discharge. So they're wearing the proper arc flash gear, went up with a temporary RFCT, clamped it on. This is an application that would have benefited from the hot stick. It could have been a little bit further away from that termination, a little bit further away from that splice. Would have been a little safer. Question always comes up: is this really effective? Just clamping something on the ground. How can that help? Here's an example from a UK utility, Electricity Northwest. If you know them, they were evaluating the technology. They took it. They tested 191 33 kV cables, and they evaluated it themselves. And they did the evaluation into 3 categories. Green means there's nothing really going on. Amber is something we should look at that a little closer, but it's not a crisis. And red means I've got dangerously high PD levels. What was unique about this is they didn't fix anything. They were evaluating the technology to see if it worked. So they did not fix the red ones or the amber ones. Within 2 years, 40% of the red categorized cables failed. 40% within 2 years. In the amber, 20% failed. And in the green, less than 2%. So what we're looking at here is if they had done what you would normally expect someone to do, I got something in the red, I'm going to fix it. Just the reds, their failure rate would have basically gone down to 1/3. And all they would have had to address is 17 cables out of 191. So, and if they had done the yellow and the red, they would have gone even lower. So there, as you stand there and you look at 191 cables, I don't know what to do. I don't know which ones are going to fail. I can't take an outage on any of them. I'll do nothing. That's what happens. Here, I do the test. The test is quick, easy. The repairs may not be, but it's always preferable to do a repair than to wait until it fails and then get called out in the middle of the night, because like babies, cables fail. Cable failures come in the middle of the night. One big advantage of online versus offline testing, the number one advantage of not doing offline testing is you don't need an outage. You don't have to convince the operators to let you take this cable out of service for 4 hours. But the equipment is a lot smaller. So when you do an offline test, you still need to energize the cable. The cable needs to be at line voltage or even higher. And so you need to bring in equipment capable of doing that. Typically that's done with VLF test sets. They're big. They can be man portable for up to say 30, 50 kV, but beyond that, we're talking truck mount. The picture in the lower right is there's over 300 kV cable in New Jersey, and there was 3 tractor trailers full of equipment to try and energize it at power system frequency. On the left is online test equipment. It's small, it's handheld. We're not energizing something, so I don't need to create 33 kV. I'm on the ground, so I don't need to be insulated from the conductor. So you've got much smaller, easier to use equipment that is cheaper, safer, and faster. What are we looking at data-wise? We've got first a phase resolve pattern, and this question came up yesterday. These numbers along the bottom, where the phase angle is, we do not align to a specific phase angle. So these blue dots occurring, it looks like it's between 0 and 90. We really don't know that. It could be anywhere in that frame. What we are looking at is that we've got 2 groupings, half a cycle apart. Opposite polarities is really good, right? We got something on a positive half cycle and something on a negative half cycle. Each one of these dots represents a capture that we took, and so clearly something is going on in this picture that is synchronous with the 60 hertz, synchronous with the power system frequency, and is occurring twice a cycle and is opposite polarity. There aren't many things that'll do that. That's a very clear picture. Here is a shot of the waveform. So each one of these dots can be looked at. You can actually see the waveform. This is that unipolar pulse that I was talking about. So you're going to look at anything. This looks like it's phase shifted, but again, we're not phase aligned. We got two groupings of discharge. They appear to be bipolar because of triggering and ringing that might occur. And we're going to look at waveforms. See here, we've got some ringing, but we're largely unipolar, much higher in one polarity than the other. If I look at this picture here, I've got no pattern, which tells me I'm not synchronous with the power system. I'm totally random. Certainly my waveforms don't look like the other waveforms. I can look at this and say that this is not PD. Whatever I've captured is noise. When you look at motor drives, you get the 6 poles for motor drives. They are electronically controlled to be a very narrow phase angle. They occur at a specific phase. And so I've got very narrow vertical lines. They're also a lot slower. It's electronic noise, but it's not nearly as fast as PD. So I'm looking at nice, slow-moving pattern in the waveforms. I can tell you this is not PD. Now, sometimes you get both. So here we've got clearly some machine drive noises, and we've got something that looks a little bit like PD. So in that case, what we'll do is we'll filter it, and we can filter it down and remove everything below 500 kilohertz, and the lower frequency machine drive noise goes away, and now I can clearly see that I've got two grouping half a cycle apart. So in summary, what we're looking for is two groupings half a cycle apart, hopefully opposite polarities. Looking for very fast rise time, unipolar pulses. And when I see that, I can rule out a lot of other causes of readings. So even if I might be reading thousands of picocoulombs, I've got to see the pattern. I've got to see the waveform before I'm even going to start to get excited about it. These limits, we got the question yesterday about standards. There are no real standards, international standards on what's a good and what's a bad picocoulomb rating. These are numbers that we have generated over thousands and thousands of cables that we've tested. They're much higher than you would see in a lab environment, but they're places where we see degradation. When you take these cables apart, you can see that they're getting close to failure. So this is a good rule of thumb. The IEEE 400.3 standard is being revised, and there may be numbers in there when it's done, but I'm not sure when that's coming out. One thing that you can do, you can always do with offline testing, and occasionally you can do with online testing, is find out how far away from the RFCT to the defect. And that is based on reflectrometry. So just like you would with a fiber or anything else, I'm looking at the reflection. So here's a waveform where I've got a direct pulse coming in. I've got a far end reflection. I've got a reflection of the direct pulse reflecting off the far end of the cable. These time differences between these two can tell me how far away it is. If you look at the cable, and we've got our discharge site again, we've got the direct pulse comes right in and through the RFCT. We've got that same pulse travels to the far end of the cable and back through the RFCT. Even the first one will go through, reflect off the near end, reflect off the far end, and back through again. And then sometimes you can see all that. Very simple math tells you how far away it is. So what we look at, T0 is the time when the discharge occurs. We don't know when that is. We don't know what the time is to T1 because all we see is the first pulse. Okay, so we call that T1. The time to the reflected pulse and the time to the reflected direct pulse allow us to do some calculations. And what we do is we basically determine how fast the waveform is moving in the cable and where the reflection occurs. And in this case, we've determined that if T2 is 3 microseconds, T3 is 8 microseconds, and we know how long the cable is. It's always important to know that. We can tell that the propagation speed is 125 meters per microsecond, and the distance to the fault is 312 meters. Now, I don't know that it's exactly 312 meters. I know that it's somewhere between 300 and 320 meters. And if I look at my cable diagram, I may find a splice or I may find a termination. That. The idea of online testing is not to detect this all the time. It's to let you go through 20, 30, 40, 50 cables in a day, rule out, like the Electricity Northwest thing, rule out 90% of them and address those 10%. And at some level, at some point, I'm going to have to take action. That action may be replacement, that may be offline testing, it may be live with it, but I know I've got redundancy. But whenever you can get a distance to a PD event in online testing, that's just a bonus. It just makes your life a little easier, but that's not really the goal. The goal is to screen high volumes of cables easily and quickly. How far can we go? We get this question all the time. How far can I see? Well, it depends on how bad the discharge is, and it depends on how high the noise level is. Paper cables have a bit more capacitance, so we use a 4-kilometer limitation as a recommendation. Polymeric cables have a little less capacitance, so you can go further with them. But if you have a tape shielded cable with corrosion on the shield edges, so on the tape edges, you know, when they put in a tape shielded cable and it's wound nice and tight, it's basically a tubular structure which has very little impedance. Imagine if those overlap points did not make contact. I no longer have a tube, I now have a big long inductor. And if I have that, I'm not going to be able to go very far at all, because I'm going to have so much inductance in the shield that the pulse is not going to get very far. Also, the PD pulse won't go past ground point, so if you have grounded splices, it's not going to go very far past that. You have about a 20 dB reduction in signal strength at each ground point. But the distances are dictated by the amount of noise, the size of the discharge, whether the cable is grounded on both ends, the type of shield, a lot of different things. These are kind of rules of thumb in terms of your measuring. We talked about surface discharge. You do have a lot of surface discharge in terminations. And so if you have unshielded cables or you have termination issues here, in the lower right appears to be unshielded cables. This white powder is PD. Here they have shielded cables, but they're above the shield is where they've got it too close together in a trifurcated cable. Same with the picture on the left. Doing ultrasonic and TEV tests on those cables, on those cable termination boxes, or wherever you have your terminations, whether it's riser poles or in boxes, are other tests you should do along with the RFCT. Don't just do the RFCT test, also check the terminations. And we also said that terminations are a huge percentage of where our failures occur, so we want to make sure that we're testing them. Just a few minutes on the equipment that I've talked about. This is our CableData Collector. It's a box that is made for an untrained crew or lightly trained crew to take data that is then analyzed by somebody else. The analysis, the data, the raw data is all stored in the computer, and then somebody trained, whether it's somebody at EA or somebody at your site that's been trained, does the analysis. So you can send out a lower level crew. It takes about 10 minutes to run the test. It automatically collects the data. It applies different thresholds, different filters, collects all this data, and then it's there for whoever's doing the analysis. You can, if you permanently install your RCTs, you can just plug them into this box and run a 3-phase test at once. The other piece of equipment we have is our UltraTep Plus 2. This device is made for doing switch gear and overhead gear. It does more than just cables. It has TEV and ultrasonic in it, which is good because we just talked about using that to do our tests on the cable boxes. But it also has a port to plug in an RFCT. This is going to give you instantaneous data right on the spot. You plug it in, you hook up the RFCT, and you watch it fill the screen live. And it's going to give you phase resolve plots, waveforms, a variety of algorithms that are going to try and point you toward PD or not. You can record the data and then Wi-Fi it to somebody who's an expert, or you can take a survey, and when you're all done, sit down to the computer and do all your analysis there. So it's a bit more flexible. It does more things. It does one phase at a time, so it takes a bit longer, and you're doing the analysis yourself. So those are the two different product options. They work in tandem depending on what your application is. So my last slide summary is, what did we learn? You know, a lot of HV equipment failures can be attributed to PD, and there are effective methods for testing cables for PD non-intrusively. We don't know the time to failure after it starts, so we want to look and do a little asset management and determine the critical ones that might need full-time monitoring, and then other ones that might need periodic monitoring with a handheld instrument. So those criticality and risk are going to be your approach to determine which cables get which type of monitoring. And full-time condition monitoring is going to help you with your safety, number one, financial, your network performance, your reliability. All those things are going to help. More data always helps. So that's the end of the presentation. Like I said, we're going to send the presentation out. We're going to send the video out. We're going to send the questions and answers out, and we'll also send out a link to our YouTube site with all our other webinar videos. So I'll take more questions.
All right. Does the RFCT require single point ground of shield? What if grounded at both ends?
It doesn't require it. If you have cable shielded at both ends, you will get some division of the PD current, and it's going to be less sensitive. But then you can also test it at both ends. If you have a single point cable with an SVL on the far end, you're going to get all the current going through the ground shield, and you only need to test it at one point. You can't test the other end.
Is there any length limitation of the cable with the testing? Also, will it provide approximate location to the fault? I think this came in before you touched upon that.
Yeah, I think I answered this
Bill,
question.
you can ignore this question. This I put in before it was covered.
I figured that question come up. That's why the slide was there.
Yeah.
We see about 25% of the time online that you get a big enough reflection to calculate the distance, because when you do an offline test, you lift both ends of the cable, you have a very abrupt change in impedance, and that's what causes a reflection. When you're online, you have a less of a difference in impedance, so you get a smaller reflection, plus you have a higher noise floor. So we see 25% or so of the PD we detect, you can actually determine the distance, but that's not the real goal.
Thank you.
Sure.
What communication technologies are predominantly used in sending the captured waveforms for analysis?
With the RFC with the CableData Collector, it's collected locally on the PC, and a zip file is created by the software. And we use whatever method is easy for your organization. If you're sending it to us, Dropbox, Google Drive, OneDrive, whatever works for you. We don't have a communication media for sending it continuously. If you're doing continuous monitoring and you have a continuous monitoring system, then we'll do an internet connection up to our cloud servers, and the system will send the data up automatically, but you'll need some sort of web interface or some sort of internet interface.
Are Rogowski coils effective for measurement?
We have not used Rogowski coils, and I don't know that their frequency range, we're looking up in the 20, 30, 40 megahertz. I don't know that Rogowski coils go that high. I'm not an expert on Rogowski coils, but I think they're more of a under 1 megahertz sort of device.
Does PD measurement have voltage limitations?
Well, since we're with cables, we're looking on the ground. It doesn't, from a safety perspective, it shouldn't affect it. Now, PD is a voltage-driven event. When the voltage is higher, you'll get PD. When the voltage is lower, the PD may stop. So doesn't affect the measurement, but it does affect the presence of PD or not.
On cables longer than the length limitations, can you confirm the RFCTs are still effective to see into the cable up to the limitation?
As everything in the PD world, there's no hard and fast numbers, but you can see PD that might occur. Yes, it doesn't, because the cable's longer, doesn't mean you won't see it. It just means if it's past the point where you'd see it, you're not going to see it. But if it's within that first few kilometers, yes, you will definitely see it.
Does the UltraTev Plus 2 require calibration?
Yes, it does. We calibrated New Jersey. There's also calibrations in England, Singapore, and Australia, and we like to see it every year because it's handheld. It gets dropped. It gets bounced around. We like to see it once a year.
Could you please talk more about the safety concern when using the RFCT?
Sure. So RFCTs, we're attaching them to the ground, and you would think that is 100% safe, but you have a couple considerations that you need to worry about. And one is the ground strap itself cannot part. So you cannot have a situation where the highest fault current that you might detect might occur through the shield cannot be more than that cable can carry. Because you don't want to have the RFCT mounted on the ground strap and then have the ground strap fail between the RFCT and ground, because then the RFCT is going to be at line voltage. You don't want that. So you want to make sure you've got good solid grounds that are designed to handle more than the worst case ground fault current. You also don't want to mount your RFCTs up at the termination end of the ground strap because of two reasons. One, that leads you to more risk if the ground strap separates, and two, we've seen customers that mount them up near the termination point, and the presence of the RFCT actually caused partial discharge. So it got into the electric field and caused PD. So you want to mount them on good ground straps, and you need to mount them as close to the ground bar, as far away from the termination as you can. Okay.
And that looks like the last one, Bill.
Okay. Well, thank you everyone for attending. I'll be sending out some information shortly, and it'll take me a little while to get the video processed, but when that's all done, I'll send that around as well. Thanks again.